We've heard about PageRank in the very early lectures as a way of finding which web page is most important. PageRank is really a property of a graph and the graph structure. This is an example of one of the ways of computing the PageRank, and it's a bit complicated, so I'll go through it a bit slowly. So the goal is to compute the PageRank for every node in a vertex. So if there are n vertices in a graph, then there will be n values pi, one for every vertex. Further, every vertex has L outgoing edges. So L of j is the number of outgoing edges that vertex j has. Right? Now, the way you compute PageRank, one of the ways is you start off with some random values at every vertex for p, just make everything 1 or half, or typically 1 by n is taken as a starting point. And then you do this kind of an update. So p of I at the next step becomes p of I times a factor. Typically d is something like 0.85, so this becomes 0.15 over n. So it's p of I multiplied by some factor plus d, which is say 0.85, times the sum of the page ranks of all the vertices that point to I, that's j is pointing to I, divided by the number of links outgoing from j. So if there's a vertex j which is pointing to I, which has a huge number of outgoing vertices, so that I is very unimportant for that vertex j, it's just one of millions of outgoing vertices for j, then its page rank when it flows into j is not considered very important. However, if I is the only vertex that j points to, then L is 1, and its importance is much higher as it flows in to I. So that's the intuition that if I'm being linked to from a page, its importance flows to me in a proportion to how important it thinks I am, which is measured by what fraction of the total edges that it points outwards to am I. That means I just divide it divides its page rank equally along all its outgoing edges, and I get that fraction of it. So if you iterate this again and again, ultimately these p's converge, so they all settle down into a fixed value, so they don't change after some time, and that value is the page rank of vertex I, and similarly for page rank of vertex j, etc. It's also a global iteration because all the vertices are exchanging messages. Now let's see how you would do this in Pregel. So if I'm a vertex, I have some estimate of my page rank, initially some random value. I send my value divided by the L, which is the number of outgoing edges that I have. I send it to everybody that I can see as on an outgoing edge, and then I look for incoming messages that would come from other vertices, and then conduct this iteration. In other words, I collect all the incoming messages from all my incoming edges, and I simply add them up, multiplying them by d, and add them into 1 minus d by n times p, and replace p with this value as per this formula. After a fixed number of such super steps, for example 30, which is often sufficient, when we can stop and the page rank should have converged. On the other hand, we could conduct a convergence test to make sure that successive p values are hardly changing at all. But then we have to do a little bit more than is provided by the Pregel model that we have covered so far, which is that we have to see whether the maximum difference between successive values across all vertices is still small, and that is the process of aggregation. Pregel allows for aggregation, though we are not going to cover that feature in much detail here. I will cover it shortly. To see how this works, there's a sequential implementation of Pregel, or the Pregel model, a very simple sequential implementation at this location, and I'll show you that code and how it computes the page rank, and I encourage you to study that and modify it to compute a few other things to get to know Pregel a bit better. Here is the lightweight sequential simulation of Pregel from the link that I just mentioned. As you can see, it's a toy single machine version of Google's Pregel paradigm. Clearly, it's not for large scale processing, it's just a simulation. Let's see how it works. It has a class called vertex, which has its obviously various things, including the value of the vertex, as well as a list of outgoing vertices. That means the IDs of the outgoing vertices also keeps track of things like incoming messages and the number of super steps being performed. Then Pregel, which is the class which does all the work, first sort of does things like partitioning the vertices across different workers, and each worker actually is performing super steps. So if you look at the super step itself, the super step essentially looks at every partition and tells the worker to do its work in every partition, and the worker essentially ends up running a super step, and the super step in the end, after all this class hierarchy, essentially for all the vertices that it happens to own in that partition, it calls vertex.update. There is no function vertex.update provided in this class, and that's the function that you as a programmer have to write by subclassing vertex with a class of your own and providing that update function. I won't go into the detailed implementation of this. I mean, those of you who know a little bit of object-oriented programming, it's fairly straightforward to figure out what's happening in this code. What we will do is look at how this basic Pregel module has been used to simulate the PageRank program, which we just described in our charts. So if you look at the PageRank program using this module, essentially you import this module and then you essentially write a PageRank vertex class which subclasses vertex and or inherits from vertex, and then you implement the update function. So what does the update function do? Very similar to our chart. If the number of super steps is less than 50, it changes its own value to 0.5 by n times 0.85 times sum of everything that it gets from the incoming vertices. And then it sends its own PageRank value out after dividing by L. So very simple. And then it stops. After 50 steps, it stops. There's no convergence test in this example. So when you run this, the way you run this is you essentially call this program which says with instance of Pregel with the number of with a list of vertices and the number of workers that you're trying to simulate. Then you say run and then return the values of all the vertices. Right. The main program essentially just creates vertices, creates edges. There's a function below there which creates a random matrix, a random graph of 10 vertices with each vertex having 4 random edges, and then you simply say PageRank Pregel, which is this function on the number of vertices, and you're done. Let's see how that actually works. So if I call that program, it computes the PageRank of a random graph. I have no idea whether this is a good PageRank. So there is actually a test provided. So what the test does is it uses a closed form formula for the PageRank, which is not an easy formula to compute because it involves the inverse of a matrix, but it's there on Wikipedia if you want to look it up. It computes the test PageRank and then compares the PageRank computed using Pregel to the test PageRank and looks at the difference. So if you if you run this program after uncommenting the test part, you see that the difference between the two PageRank vectors is very small. So the This one was the Pregel computation of PageRank, the test computation, which is using the closed form formula, and we get the right answer. Returning now to the Pregel module itself, one interesting exercise that some of you might want to try is see whether you can actually write a parallel version of this program, possibly building on some of the way mincemeat.python actually built a lightweight parallel implementation of MapReduce. That would be an interesting contribution to the open source community if any of you are interested to try it out.